We now have a look at one of the fundamental procedures, and that is taking two sorted arrays A and B and converting it into a sorted array C. So what we take as a procedure over here is taking the first element in A and this first element in B and comparing them. Whichever one is smaller is pushed into C. And now the element which has been pushed in is removed from the corresponding array. Let us say B was the element. So B's pointer goes forward to its second element, and now its second element and the first element of A will be compared. Whichever one is smaller is pushed into C, so on and so forth till C is complete with elements from A and B. And now you can say that we have sorted these two arrays. We have merged these two sorted arrays. So the overall time requirement for this procedure is order n. As we have seen, asymptotic optimality does not necessarily mean practical optimality. So we can do better here. And let's try to think about logically improving this procedure. One of the things that might happen is that comparing the first element of A and first element of B might not be the most optimal way. If we can find the corresponding position of A in this sorted array B, then what we can do is we can take all elements. Let us say A, the first element of A lies over here. This is the corresponding index of the first element of A, let us say X. So X should lie over here in this index in the array B, which means that all elements before this index are smaller than the first element of A, which means all these elements could have been directly copied onto the array C. That would save a lot of comparisons. It would still require the assignment, it would still require copies, but copying is much cheaper than a comparison operation. So a lot of comparisons would have been saved had we used this procedure. So why don't we just use it? We'll have a look at why this may not be the best thing, but let's try. If we do this, then we take all of these elements, let us say from index 0 to 4, and do a system array copy. So this is going to be pretty fast because it's just copying elements, and that's 5 elements we have copied for just one comparison. This comparison is hiding some information. It's not just one comparison, so to speak, it's finding the corresponding position of X. So finding the corresponding position of X will require a binary search in the second array, and that is in fact log of size of B comparisons, and that is around log n comparisons. So it's pretty large in terms of number of comparisons being done. Now, what happens if you're not skipping many elements? What happens if you're skipping just one element? The corresponding position of X was the second element in array B. In that case, for every log n comparisons, you're just getting 2 elements being pushed into the array C. This means that for every 2 elements in B, so that is in the worst case n by 2 times, we are doing log n comparisons. And this is order n log n, which is pretty bad because we already know that the optimal is order n, and we are trying to improve on this, not here. Okay, so what we are seeing is that if this number is very small, if this number is lesser than log n, then it doesn't make sense for us to actually apply this procedure. Instead, we should use this brute force way of comparing the first element here and the first element here, and then copying the smaller one, and then keep heading in a linear fashion. However, if we are getting benefits of at least size log n, every chunk that you are able to pick up from here, every run that you have is of size log n, then we are actually benefiting from using this procedure of finding the corresponding index in the next array, copying all elements before it onto the resultant array, and then using the remaining arrays in the new procedure. So effectively you have B starting over here now. An additional and similar improvement in this is to find the position of the last element in A. So let's call it Y, and we find the last element position of Y in array B. Let us say it belongs over here. So all elements beyond this index are in fact greater than Y. So what we could do is we can take all those elements and directly copy them onto the resultant array, which we'll have in the end, we'll be returning in the end. And what we'll be left with is these elements have to be correctly sorted, have to be put in this in the corresponding positions in C, and these elements have to be put in the corresponding positions in C. So that will be this space. But the good thing is we have actually skipped all the computations that we had to do, all the comparisons we had to do for the extreme values of A, which is X and Y. So that's some saving. And how much is the saving? Well, we can't say. It depends from array to array. If we are finding some benefit by doing that, we should. If we are not seeing any benefits, then we shouldn't do it in a recursive way. Another thing to note is that when we have the elements actually copied over here, we are guaranteed that X is larger than the first element over here. So we should actually copy X also over here. This is X. And Y is smaller than all elements before this element. So Y will be copied in the end. So I can put Y over here. And it's effectively, these three elements are copied and Y is copied over here. And what we have remaining now is this portion, which has to contain all the elements between X and Y, So what we are seeing is that there's a procedure to potentially reduce the runtime when merging two sorted arrays. And this is not giving us any guarantees. However, in the real world, there's a lot of data which is partially sorted, which means that there is some sort of ordering in the data. And as you can see over here, if there is some sort of ordering in the data, if this element is much larger than the first element over here, which means it will skip a lot of elements, then we can take advantage of that to reduce the number of comparisons we have and just convert them just to assignments. You copy from this point to this point, and this is usually very efficient because the operating system itself gives you ways in which you can copy arrays from one point to another onto a resultant array. So array copies are pretty efficient. And as you're seeing that we can do this on the other end of the array also. If we are smart about this, then this could potentially reduce a lot of the time complexity we have. Now let's try to get into some detail in terms of comparing which operation will be better. Is it finding the corresponding index and copying stuff, or is it just doing the brute force way, the standard merge sort way that we have for merging two sorted arrays? So the first thing that we can do here is to think about what are the benefits of doing it in the standard way, in the conventional way. And the first advantage is locality of reference. Because the two pointers are heading forward by just one position, the operating system can make predictions as to which element needs to be pulled out from the array next. Because they're going one by one, it can tell that maybe the next element has to be picked up, and based on that it can pick up the next 5, 10 elements. And every time you're making a read operation, it's actually very efficient because it's already in cache. Okay, that's one of the things, locality of reference. The second thing is simplicity. And simplicity not just in terms of code, but also in terms of the number of variables you need to actually run this procedure. Because binary search by definition will require some sort of left, right. It requires a range, and it also requires then which element will be in the middle, and it gets a little complicated. So you need more variables for binary search, while the two-pointer approach is extremely simple. It just needs two variables and they are heading forward one by one. On the other hand, there's some advantages of finding the corresponding index also through binary search. The first one is potential runs are large. So maybe you'll be able to skip a lot of elements, and binary search can give you that. Maybe the corresponding index is far ahead for X, which means that you save on a lot of elements. And the second thing is comparisons are potentially reduced. So you're seeing that both the advantages are mainly about potential over here. So what we would like to do is have an intelligent algorithm telling us when to do a binary search and when to do conventional merging. When it comes to intelligence and algorithms, the first point is artificial intelligence, and a subset of that is machine learning. So can we actually read the data and figure out what we should apply as a policy? Should we apply finding the corresponding indexes, or should we apply the simplistic approach? Instead of thinking about artificial intelligence though, when it comes to sorting data, it's something that you want to do really fast, and you can't really train neural networks for this. So we have one parameter, which is galloping threshold which will define the intelligence of our algorithm, right? This is something that the algorithm will be using to make decisions. So it's initialized to 7. Now, galloping is the process of taking elements in B and just moving forward up till the corresponding point X belongs in. And similarly, going from the back end and moving backwards till you hit the point where Y belongs in the corresponding array B. So this is a gallop because you are not moving one by one. It's not like a walk. This would be a walk. The standard procedure is a walk, and just charging forward on a horse, so to speak, is a gallop over here. So initially the galloping potential is set to 7, which means that if you get to skip at least 7 elements by finding the corresponding index of X in B, then it was a successful gallop. Otherwise, you got onto the horse. By the time you got onto the horse, by the time you moved forward and got down from it, the time requirement for that expensive horse climbing or binary search operation over here, this is pretty expensive, log n. By the time you did this, the advantage was lesser. So your gallop, your run, your chunk, whatever you like to call it, has to be greater than 7 for it to be beneficial to you. And galloping threshold is set to 7. If you find that this chunk was of size greater than 7, what we do is we subtract from this threshold. We make it 6. The reason being that this array seems to be promising when it comes to galloping. The corresponding index of X was over here. Next time maybe the element Z will be found far ahead. We are going to make an assumption. We are going to say that galloping is helping us in this array, and we are going to do more of galloping. How? By reducing the threshold. So next time, even if you have just 7 elements, it's not greater than 7. Even if you have 7 elements, it's enough for you to do a gallop. And again, then if you have just 6 elements, when it turns to 5, you can do a gallop. However, now let's see what happens if you have just 2 elements. Okay, and your gallop threshold is 5. You have just 2 elements. This means that we got onto the horse, came down. It's like the binary search was really expensive compared to the number of elements we got to skip. So the galloping threshold should deter you from galloping next time, which means it should increase. And it goes up to 6. This looks pretty confusing. Let's have a look at how an example works. So I'm going to give it a threshold, a galloping threshold of 4, because this board doesn't have that much space. So galloping threshold of 4 means that if 4 elements are skipped, then we're good. Then there's a good gallop. So finding the corresponding index of this is going to be coming to the center, doing a binary search, and we are effectively going to land over here at element number 5. So this is the point where 1 should exist in B. Now all elements before this point are definitely smaller than 1, which means that we can just do a system array copy into the resultant array C in this way. Copying minus 15, copying minus 12, copying minus 8, and copying minus 7. So these are the indexes from 1 to 3, 4 elements. Now this also means that the element over here is greater than or equal to the element over here, which means that this element should just be copied onto this point. Alright, so in total there are 5 elements which have been pushed in, and these 4 were galloped into. These 4 elements were not compared with anything. Cool. The similar case is done with the last element in A, 10. Corresponding index is found to be for value 40 is found to be over here. It should exist on 44, which means that all elements after it are smaller than 40. That also means that all elements over here from 7 to 10 can be directly copied onto the resultant array starting from the end without having any problems. So I'm going to do that. I'm going to say that copy 40, copy 79, 60, 57, and 44 with impunity. There's no worry over here. And the total number of elements we'll have after this operation is over is 11 plus 11, which is 22. So index number 21 will have this 20, 19, and 18. So these are the advantages we have. And of course, this element is greater than all elements. Rather, this element is smaller than all these elements, and these elements are all smaller than 40. So the next element has to be 40, so we are going to copy that also at index position 17. So what we have done now is to get rid of all elements from 1 to 1, from 40 to 40, and get rid of these elements up till 12. 12 is still in contention, and 35 is still in contention. So this range is remaining, and the entire range of the earlier array is remaining. Effectively, what we have done is we have converted the array B, starting from here and ending over here. Right? That's what the array B is now, instead of this large array. And A has been converted starting from index 1 to index 9. So recursively now we can do the same thing. Array B is smaller, so we should probably use we should find where 12 exists in the array A. And so you can see that recursively, if we do this, we are going to actually save on a lot of computations by just doing binary searches. Okay, so this is a good example of galloping. And in this case, after the gallop is done, after we see that there have been advantages of doing this gallop once and twice, the galloping threshold will reduce to 3 because galloping is helping us. Okay. In case galloping is not helping us, which is going to happen right now, I'm going to be choosing purposely an array which is really bad when it comes to galloping. So let's take the elements such that they are very close to each other. So there'll be 2 over here, there'll be 4 over here, I'll put in 6, I'll put in 10, and then I can have 19. So if you observe closely, you'll see that these elements are being chosen so that it's between these two elements. 19 is between these two. I can have 25 between 22 and 30. These two elements are too close, so I'm just going to put in 30. And it's like a destructive way to think about how do I break this algorithm so that it performs really poorly. So 32, 33 and 36 is 35. And then I can squeeze in between these two elements is 38, and finally maybe 42. Okay, so now we have a new array. Let's see if our algorithm does nearly as well. The first element that we are picking up again from A is 1. 1 is the smallest element in array A and also the smallest element in array B. The corresponding index of this comes down to 0. If it existed, it would have existed here, which means that all elements before it, which is nothing, have to be copied onto the array C, which is nothing. So the gallop was really bad, and if I start with a galloping threshold of 4, it does not meet the galloping threshold because the number of elements is 0, galloping threshold is 4, that is greater, so I punish my algorithm for even trying to gallop by putting it at 5. So next time you try to gallop, you at least have 5 elements before you even think of it. All right, and what's happened will be also from the reverse side. The same thing happens. If you have 40 over here, and we see that the only element that we are able to skip is this element. The corresponding index is over here, 40, and one element is skipped. So galloping threshold actually had not been modified. The total number of elements are what defines the galloping threshold. So we have on the left hand side 0 elements skipped, and on the right hand side we have 1 element skipped. So 0 plus 1 gives us 1. Galloping threshold is 4, greater than 1, so we punish ourselves and we say it's 5. But of course, because we have galloped, we just use the element 42 to be copied onto index 21, and we also know that 40 has to be copied over here. We are not sure about these 3 elements. On the other hand, the first element is also skipped because, yeah, it's the smallest element, so we can copy that 1. And effectively what we have is these 2 elements on the edges are kicked out, while B is from 0 to 9. It's almost entirely left. Now let's have a look at the galloping threshold again. The galloping threshold comes out to be 5. And if we do a binary search, which we won't by the way, but if we do it for 3, we will see that we land over here. And there'll just be one element skipped. For 36, there will be no elements skipped. Or rather, yeah, there will be one element skipped again. So because it will land over here. So there'll be 2 elements in total, which is 2 is less than the galloping threshold, and the galloping threshold will increase. An important point to notice here is that you do not enter the galloping threshold by default. What you need to do to even enter the galloping mode is to have lots of elements coming from a single array. Because the galloping threshold is 5, you need at least 5 elements consecutively from either A or B before you enter the galloping mode. So assume that if we got 3 as the next element to be copied, or let's say 2. 2 is the next element to be copied, so 2 comes over here. And for some example, assume that 4, 6, 10, and 19 come in. At this point, we see that the second array is continuously contributing to the resultant array greater than the galloping threshold. The number of elements which have been copied directly are greater than the galloping threshold. If this is the case, then we know that we should probably try galloping. Maybe the natural order is really nice. Galloping threshold can increase and it can decrease only up to the point of 7. Anything less than 7, and it doesn't really make sense to do the binary search. It's pretty expensive as an operation for the threshold to be anything less than 7. And this is what Timsort is. It's just merging 2 sorted arrays in an efficient way. And the way it makes it more efficient than probably using the conventional approach is to use galloping. Also, there is intelligence in the galloping by finding whether you're getting some advantage of doing the gallops. Your natural runs, if they exist, then there'll be more galloping. If lesser natural runs exist, if it's zigzag, 1, 2, 3, 4, 5, 6, so on and so forth, then this is not a gallop and you're doing something like a walk. And at that point, what happens is the threshold is so large that you fall back into the standard merge sort technique of merging. Across computer science, you can see algorithms like Timsort, which use compromise and composition to get the best results. Sorting is a very important part of computer science. So to understand it at a deep level, you need to get into the hardware specifications of the computer and the theoretical understanding of the algorithms. And once you do that, you have the best practical algorithm out there, which is Timsort. I'll see you next time.